Hello and welcome to Calculus 1. These videos will be an approximation to the material that I would ordinarily be presenting in a classroom. These videos, this series of videos, will represent the online version of my Calculus 1 sequence of lectures. And the big drawback, of course, is that while you're watching these videos, you can't exactly ask questions in real time. However, I would encourage you to make a note of any questions you have, and feel free to send me an email, and I will reply as quickly as I can, usually within a day or two. Or if I'm holding online office hours, you're welcome to ask questions then too, of course. So with that said, let's just get started. So I'm not going to talk a whole lot about the history of calculus. I'm by no means an expert, but I am aware that it came from sort of the origins of it were in ancient Greece and India, and of course Persia, the Middle East, and China, and possibly other places as well. And this was, a long time ago, thousands of years ago. So, of course, they didn't call it calculus back then. It certainly wasn't fully developed. These were a whole bunch of ideas that really didn't come together until much later. So a lot of it was very vague and not fully developed at that time. So it wasn't until about 400 or 500 years ago in Europe where Sir Isaac Newton and Gottfried Wilhelm Leibniz sort of put all of these ideas together into a coherent framework, which they called calculus. And essentially the two main branches of calculus are differential and integral. Of course, we will study both. And it really was both Newton and Leibniz who sort of put them both together and explained the relationship between differential and integral calculus. So yes, and there's a big bitter rivalry between Newton and Leibniz, and so I'm not going to get into that, but in the end, it's both Newton and Leibniz got the credit. Of course, the story didn't end with them, even though they established this powerful tool of calculus, and Newton used it quite extensively to explain the orbits of the planets around the sun, for one thing, although the planet orbits were mathematically described by Johannes Kepler a little earlier than Newton, but then Newton actually used his law of gravitation to explain why those orbits are in the shape that they are, namely in the shape of an ellipse. Right? And same thing for comets, although comets can also have parabolic or hyperbolic orbits. But generally in the shape of conic sections, right? And then sometime later, maybe in the next 100 years or so, the calculus was made rigorous into a branch called analysis, or real analysis, by players like Cauchy and Euler and Weierstrass. So they essentially made the mathematical framework rigorous by proving a lot of things that Newton and Leibniz sort of just took for granted. Okay, so I think that's all I'll say about the history. Of course, it's way bigger than that, way bigger than what I've described here. But it's not a history course. It's a math course. So let's get into the math. So first of all, right, what is calculus? right? And there's a lot of ways to answer that question. Obviously, it's a branch of mathematics. So I would describe it as, right, a mathematical description it's a mathematical description of continuous change. Forgive my sloppiness here. Continuous change. So things are changing, of course, all the time, as they should. And, right, so calculus just describes how that's possible and how quickly things change. So in particular, what we call the rate of change. It also has to do with finding areas and volumes of objects that are not just familiar to us, like, like circles and rectangles, but more complicated objects, as well as a process called summation, where you're adding things up, right? So again, this doesn't describe all of calculus, but it's a good starting definition, anyways. And one thing we're going to describe, quantities that change, and there's a lot of things that change, a lot of quantities. But one we're going to talk about over and over is this idea of motion, right? When things move, what's changing, right? Your position is changing. So it's a change of position. And as you change your position, right, you're moving. And how quickly you're moving, well, we call that velocity, right? Or speed. A lot of people use these two terms interchangeably. However, there is a difference, and we will get into that. In fact, maybe now I'll explain them a little more carefully now, right? So you know what distance is, right? Distance is how far apart two things are, right? And so speed is just how quickly that distance is changing, right? So speed you can think of as the rate of change of distance. On the other hand, velocity is also a rate of change, but it's the rate of change of position. So what's the difference? Well, right, as you're moving, if this is your starting point, however you're moving, right, the distance that you're traveling is just, right, it seems to be always getting bigger, although it doesn't have to be, right? But distance is defined to be the distance between 2 points, and hopefully you know the distance formula between 2 points. So here's a quick refresher on that. But it's a square root, right? So it's automatically positive, right? Distance is automatically positive by definition. On the other hand, your position, depending on where your starting point, if this is your 0 point here, and you move to the right, right, you're moving in the positive direction, right? If you move to the left, you're moving in the negative direction. So position can be positive or negative. And therefore, the rate of change can be positive or negative, right? So velocity, right, can be positive or negative. Whereas speed is always positive, right? So speed is always positive. Or it could be 0, of course. If you're not moving, your speed is 0. So, right, so we'll say always non-negative. Right. Essentially, right, if you're going forwards, your velocity is positive, right? If you're going backwards, your velocity is negative. And which way you say is forward or backwards is up to you, right? Our convention is typically that right is positive and left is negative. Or up is positive, right, and then down would be negative. Although that's just a convention. You can reverse it if you want, right? Right. But speed is just the rate of change of the distance you are. So, right, so that's always going to be positive. Okay. Right. So even if you're going backwards, right, the distance you're traveling is still positive. So I hope that helps. But getting back to this idea of motion, right, which is essentially things moving, changing position. I want to get into something that, again, I'll mention again in the next video, and that's this idea of Zeno's paradox. And Zeno was one of those ancient Greek philosophers that, was wrestling with this whole notion of motion, the idea that things can move at all. Seemed weird to Zeno. And again, that was a long time ago. So there's actually several different versions of this, but here's one version, right? So if you want to start at point A, right, and you want to end at point B, right? Well, let's go there in the simplest possible way, right? Just a straight line. We're going from point A to point B. Okay. But in order to do that, right, to go from point A to point B, you can't get there instantaneously, right? You can't just teleport from A to B right away. It takes time to get there, right? Now, how much time does it take? Well, let's see. In order to get from point A to point B, you have to get first to a point halfway in between. So rather than use A and B, let's call this point C, which is halfway in between, right? So before we can get to point B, we have to get halfway there. Okay, so now our destination is point C. We have to get to point C. But how do we get there? Well, we have to get halfway there first, right? So we have to get to, say, point D, which is halfway between A and C. Okay, but then to get to point D, we need to get halfway there as well, point E, right? And to get to point E, we have to get to point F, which is halfway between A and E. And, well, you can see that this is going to go on forever, right? So there's always going to be a point halfway between any 2 points, right? If I blow this up and say this is point A and point G is way over here, well, there's still going to be a point halfway in between, say point H. But to get to point H, there's going to be a halfway point there as well. So how many of these halfway points are there? Well, obviously there's no end to them. They keep going forever, right? So how long does it take to get from point A to point B? Well, you got to go through an infinite number of points. So it's going to take forever, right? So according to Zeno, motion is impossible. You can't get anywhere, right? Now, obviously that doesn't make any sense because things are moving all the time. So that's what makes it a paradox, right? So how can you explain that, right? When, right, clearly you're adding up an infinite number of numbers here. You just keep dividing by halves, but it goes on forever. Right? So you're adding up an infinite number of numbers, an infinite number of times. And so to get anywhere, it should take an infinite amount of time. Okay. But that's ridiculous, right? Obviously, motion is certainly possible. It happens all the time, right? So, unfortunately, to resolve this, you really have to wait till the second semester, till you get to Calc 2. On the other hand, I think intuitively we know what's going on here, right? You're adding up a bunch of numbers, right? So, if let's say the distance from A to B is just 1. And then to get halfway there, right, you get to the point 1/2, right? And then halfway there, you get to 1/4, right? And then 1/8. and 1/16. So you're adding up all these numbers here. And even though there's an infinite number of them, notice that each of these numbers are just getting smaller and smaller. Right? And as it turns out, when you add up 1/2 plus 1/4 plus 1/8, you actually just get 1, which is the original distance. Right? So yes, there's an infinite number of these, but because they get smaller and smaller, right, eventually they get so small that they're practically indistinguishable from 0. Right? And so you're adding up such tiny numbers that you're not going to gain anything bigger than 1 at that point. So again, I'm going to, this will happen in the next video as well, but I just wanted to give you this idea of motion and the problems that you can get by thinking about this in the wrong way, where if you add up numbers like 2 plus 3 plus 4 plus 5 and so on, when you add those up forever, you really don't get anything, right? You get infinity. But adding up small numbers, you can get a finite number. Okay, so you're gonna see that again in calculus 2, and a little bit in the next video. In the next video, the idea is kind of reversed, where we assume that you can get from point A to point B, right? But to get there, of course, you get to the point halfway in between, and that's fine. And then to get from C to B, you have to get halfway there, and so on, right? And so you can get as close as you want, getting closer and closer to B. Now, assuming that each step takes a finite amount of time, right? And let's say it's a amount of time that doesn't decrease, then you'll never get there, right? Because there's always going to be another point halfway in between. But obviously, you can get there just by adding up these numbers rather than these numbers, right? But this gives you the idea of what's called a limit, right? And this is something we will get into much more detail in the next section. It's this idea of getting as close as you want to something, but never getting there, right? So if you want to get close to a number like 0, right, 1 is pretty close to 0. But a number like 1/10 is also close to 0. 1/100th is even closer. 1/1000th, and so on. So just keep adding zeros, right? In decimal form, it looks even better, right? 0.1, 0.01, 0.001, right? And these numbers are just getting closer and closer to 0. And you can get as close as you want just by adding more and more zeros before the 1. So this number is approximately 0, but not exactly 0, right? So these numbers are close to 0, but not exactly 0. Okay, so that's an important concept. Okay, so before we get into all those technical details, and again, it might seem difficult at first, but it just takes a little time to get acquainted with all these concepts. So before we do that, maybe we should just review a little bit of some concepts that you should know by now. But if it's been a while since you've had pre-calculus or trigonometry, then this is a very quick refresher, right? So the first thing we should talk about, of course, are lines, right? And so you have your xy plane. Let me see if I can do a little better than that. All right, close enough. Right, so you have your x-axis, your y-axis, and then you want to describe a line mathematically. You could do that a couple ways. One way is to use the equation ax plus by plus c equals 0. Let me say that again. Ax plus by plus c equals 0. So this is sort of the general form of the equation. Or you can write it as y equals mx plus b. Right, so this is the slope-intercept form. Again, I'm hoping you know what slope is, but I'll talk about that in a minute. Right, and b is the y-intercept. Right. So two good ways to represent a line. Actually, this way has to be a little more specific. This is for a non-vertical line. If you want a vertical line, then you have to use the general form. Okay, so a, b, and c are just numbers. M and b are just numbers. In fact, let's talk about m right now. M is called the slope of the line, and it's a number. And informally, we think of it as, right, rise over run. It's the ratio of rise to run. So here's the run, right? And then here should be straight. Here's the rise. I know that's kind of tiny. Let me see if I can make that a little bigger. Yeah, so in order to calculate slope as a number, you need 2 points on the line, right? So one point you can call x2 and y2. The other point could be x1 and y1. And so the rise is just the difference in the y values, right? y2 minus y1. The run is the difference in the x coordinates, x2 minus x1, right? Or you can think of the rise as a change in y. So delta y is a change in y, and delta x is a change in x, right? So this triangle here is the Greek letter delta, the capital delta. And again, this just means a change in y. And likewise, delta x is a change in x. It could be a big change, it could be a small change, but it's a change, right? So that's slope, and you know how to calculate that. And b, of course, in particular, the point 0b is called the y-intercept. Right? And that's, well, I should do it in green. This point right here, right, is the y-intercept. X is 0, y is b. Okay, so going on to our next topic, something you should know about are functions. This is fun with functions, right? So you probably remember those as the y equals f of x, right? And you know by now that this is not f times x, right? If you want to read this, you can read f evaluated at x, right? Or just f of x, right? But here, parentheses do not mean multiply, right? Typically, when you see something like 3 times 6 is 18, we think of parentheses meaning something to multiply. But not here. F is not a number, right? X might be a number, Y might be a number, but F is just the name of the function. It's a label, okay? So, yeah, so please do not even think that this is F times X. Don't say that. Don't think it, right? So what we're doing here is we're taking x as a number and plugging it into the function f, right? So this box is labeled f as function, and it takes x as an input, and then it produces an output, which we call y, or just f of x, right? So yeah, y is the output, x is the input. And when you take all possible x's, right, the set of all inputs, right, we call that the domain. And then the set of all the outputs is called the range. Actually, it's called the codomain, but we're not going to get into that. For our purposes, if you take the set of all outputs, it's the range. The issue is that you can have numbers y that are not formed from x, that are not outputs with x, but nonetheless you can still consider them to be in the range. So let's not worry about that. That's not going to be a big issue going forward. So just realize that, right, the set of all outputs is a pretty poor definition of range, but for our purposes, it's not going to get us into trouble here. So let's maybe just look at some examples. So you can have f of x just might be, x squared minus 3x plus 2. Right, so this is a quadratic function. You've seen these before many times. So when you write f of 4, You know what that means, right? You just replace all the x's with the number 4. So 4 squared is 16. 16 minus 12 plus 2. So we get 4 plus 2 is 6. Right? So if you were to graph this function, and you know the graph is a parabola, right? Then the point x equals 4, y equals 6 is on the graph. Right? It's one of the points on the graph. Okay. Something else you should know about, that you don't have to replace x with a number. It could just be a letter, right? Like h. So that just means you change x to h. So you get h squared minus 3h plus 2. Right? Or you can turn it into something more complicated, like, like x plus h. And to calculate that, you replace x with x plus h. Don't forget to square it. And then subtract 3 times x plus h. And then just add the 2. So you might want to expand all this out, right? So this is going to be x squared plus 2xh plus h squared minus 3x minus 3h plus 2. And I am not going to explain this after this, but if you're wondering, where did I get the 2xh, right? I thought x plus h squared, hang on, I thought x plus h squared, isn't that just x squared plus h squared? Really? So I hope you're not making this mistake anymore. It's a fairly common mistake, right? Don't feel bad if you make it, but at this point you really should get over this, because this is not good. Right? What do I mean by x plus h squared, right? I mean x plus h times x plus h. And when you write it this way, right, this should remind you of our favorite 4-letter word here, right? FOIL, right? So FOIL stands for first, outside, inside, last. The first 2 terms is just x times x, which is x squared. The outer terms, you get x times h. And the inner terms, the inside terms, you get h times x, but that's also x times h, right? And then the last 2 terms, h times h, you get h squared. So when you add 1xh plus 1xh, you get 2xh. And again, you should know that by now. If not, make sure you don't make this mistake again, right? You don't get x squared plus h squared. You got to get the cross terms, the xh and the xh. Okay, so with that in mind, now let's get on to the difference quotient, which is also an important concept. Right. So you've seen difference quotients before, and they look like this. So you get f of x f evaluated at x plus delta x minus f of x over delta x. And depending on where you took your pre-calculus course or with what book, you might see it written differently. You might see it as f of x plus h minus f of x over h. So yeah, whether you call it h, right, or delta x, it's really the same thing. Our book tends to use delta x, so I'm going to stick with that. Okay, if you want to use h, go right ahead. That doesn't bother me one bit, right? But when I write it, I'm going to use the way the book writes it, so you don't get totally confused. So as an example, let's calculate the difference quotient. So find and simplify, and that's the hard part. Simplify the difference quotient. I'm going to abbreviate difference quotient for f of x, and we'll use the same example, right? X squared minus 3x plus 2. Right, so this is something you've done many times already, or at least I hope you have. And it starts, let's just write down the difference quotient. It's the definition. And now we apply it to this particular function, right? So wherever you see an x, you trade it with x plus delta x. Again, you can use x plus h like we did up here, but if we use x plus delta x, what do we get? We get the quantity x plus delta x squared instead of x squared, minus 3 times x plus delta x, and then plus 2. Right? And then minus f of x. So f of x, I can just copy that down here, x squared minus 3x plus 2. Everyone okay with that? So, so this part here is the f of x plus delta x, and then this over here is the f of x, so you don't get confused. And then we're dividing the whole thing just by delta x. Okay. Right. So obviously this is the difference quotient, but we're not even close to done, right? We have to simplify this, right? So let's expand out the numerator as much as we can. The x plus delta x squared. Remember, that's x squared plus 2x delta x plus delta x squared. I'll use parentheses, right? Minus 3x minus 3 times delta x plus 2, and then minus x squared. And then don't forget to distribute the negative sign here to each term inside. So we get a plus 3x and then a minus 2, all over delta x. Okay, so that's a lot better, right? And in particular, notice that I have a positive 2 here and a negative 2. So 2 minus 2 is 0, so they just add up to 0, right? So you can say that they cancel, right? We also have a negative 3x and a positive 3x. That also adds up to 0. And we have, well, negative x squared and positive x squared. That also adds up to 0. So a lot of things cancel in the numerator, and what are we left with? We're still left with 2x delta x plus a delta x squared minus 3 times delta x, and that's it, right? So divide by delta x, and there's a couple ways of working this out. My favorite way is to notice that in the numerator here, we have a factor of delta x, another factor of delta x, and another factor of delta x. So let's just factor out that delta x. So what does the delta x multiply? So it multiplies the 2x, and since this is delta x squared, it multiplies another delta x, and here you're multiplying just the negative 3, all divided by delta x. Okay, right, and now we're almost done, right? Next thing to notice is that delta x divided by delta x is 1, so they cancel, and we end up with 2x plus delta x minus 3. And that's as far as we can go. This is the difference quotient of x squared minus 3x plus 2. Okay. Oh, we should mention one thing here. We're assuming that delta x is not equal to 0, right? So we can only cancel the delta x if it's not equal to 0. So that's important, right? Yeah, because if delta x is 0, we get 0 divided by 0, which is nonsense, right? And maybe now is a good time to mention that. Whenever you see 0 divided by 0, right, it's not a number. It's meaningless. It's undefined. Or specifically, it's indeterminate. Right? It could be anything. It could be anything you want, right? And therefore, it's not a well-defined operation. 0 divided by 0 just doesn't make any sense. Mathematically, it's nonsense. So we can't do anything with it. So if you see 0 divided by 0, just cross it out and figure out some other way to do the problem, right? Because 0 divided by 0 could be any number you want it to be. And so it's not helpful, okay? Yeah, so that's effectively what would happen here if delta x equals 0. The original expression would also equal 0, because you get f of x minus f of x, which is 0, divided by 0. So 0 divided by 0 doesn't mean anything, right? Oh, so I'm going to refresh this. Right, so next thing we can do with functions is that we can compose them. Right? We can take what's called the composition of functions. We have two functions, f and g, right? And they could be the same function, but usually they're not. Usually they're two different functions. And I'm assuming that you know how to add two functions and subtract two functions and multiply two functions and divide two functions if appropriate. But this is none of those, right? This is composition. Okay, so be careful, right? This expression here is not f times g. You're not multiplying them here, right? Right. If you want to multiply them, you would write f of x times g of x, right? But this is f of g of x, right? So so this is f times g here, right? But not up here, not the one in blue. Right. So what is composition? It's just essentially chaining two functions together, one after the other. You take your x, that's the input, right? And what is x doing? It's going into the function g. So x is the input of g. So here's the function g. X goes in, and what comes out? Well, y, or in this case, g of x. Right? That's your y value. Right. Now, g of x, that comes out of g, and then it goes into the function f. So the output of g becomes the input of the other function f. And what comes out is f of g of x. Right? So it's a two-step process, right? You're taking x, goes into g, what comes out is g of x, and then what goes into f is g of x, and what comes out is f of g of x. Okay, so yeah, I think a good example will help here, right? So let's suppose f of x is just the square root function. Right, so square root of x. And let's suppose g of x is, oh, I don't know, how about 3x minus 2? Okay, so let's find f composed with g of x. Right, and while we're at it, we can go the other way and do g of f of x. Just go backwards. Right. So first of all, let's just write down what this means, right? It means we're taking f of g of x. And to be fair, I don't think the book uses this little circle notation for composition. A lot of books use that notation, but our book just tends to write it this way, f of g of x right away. So I think that's probably good practice. So there's no point in writing it this way. We could just write it f of g of x like this. Right? So I would do it this way. I would say, look, what does f do to x? It takes the square root of it, right? So what does f do to g? It does the same thing. It takes the square root of g of x. Right? So you just take the square root of whatever's in the parentheses. In this case, it's g of x. Now, what's g of x? Well, it's 3x minus 2. So you just take the square root of that. That's all it is, right? If you want to go the other way, take g of f of x. So I would say, what does g do to x? Well, it multiplies it by 3, and then it subtracts 2. So what does it do to f of x? The exact same thing. You multiply f of x times 3, and then take away the 2. So what's f of x? It's just the square root of x. Okay, so that's g of f of x. Right? And you'll notice that this is not the same thing as the square root of 3x minus 2. Right? So in general, if you take f of g of x, that's not going to be the same as g of f of x. Usually not. Although, sometimes they are equal. And in fact, you should know when these are equal. Right? In fact, well, okay, so I suppose when they're equal, they don't always have to equal the same thing. But let's suppose they're both equal to x. If they're both equal to x, you should know how f and g are related. Okay, so if you forgot, f and g are inverse functions. Right? So this is something we will talk about much later, toward the end of the course. But hopefully you remember what inverse functions are. If not, I'll give you a very quick refresher when we get to it. This is way back in Chapter 5, so this will be toward the end of the semester, toward the end of the course. But yeah, so obviously these two functions here, f and g, these are not inverse functions. Because when you compose them, you don't get x. You don't get the same thing. Okay, and so similar to this is instead of taking two simple functions and composing them into a more complicated function, you should also be able to go the other way. So for example, suppose we have a function, I'll call it h of x, and yeah, let's say it's, oh, I don't know, how about 3x squared minus 5x plus 1 to the power 7. Okay, so rather a complicated function, but it turns out to just to be a polynomial function. You know, if you were diligent enough to expand all this out as a polynomial, yeah, that will take a lot of work and a lot of time and a lot of effort, and it's not really worth it. So let's not do that, right? But we can think of this as two simpler functions, right? We can think of, right, this function as a composition of two other functions, say f and g. So what's on the inside of the parentheses here? On the inside of the parentheses is the quadratic, 3x squared minus 5x plus 1. Okay, so what does f do to that? Well, we have to take the 7th power. So f should just take the 7th power of whatever's in the parentheses. Right, so this is one way to decompose these two functions. Right, we decompose this function into two simpler functions. Right, and this is something that you're going to do over and over, many times without even realizing it. Right, but you know, explicitly you could write out what f and g are. Over the course of the semester, you should really just get used to this and think of this as a composition. So this will become second nature eventually. And then we get to the trigonometry. Yep, you got to know your trig, right? Your sines and cosines, right? So sine of theta, cosine of theta. And you should know the relationship to the unit circle. Right? So you draw your xy plane. Say this is the circle of radius 1. Let me try to draw a better circle than that if I can. All right, close enough. Right. So you have some angle to the positive x-axis. That's the standard position for our angle. Right? And then where this line crosses the circle, at this point right here, well, you have a point, right? You have an x-coordinate and a y-coordinate. In terms of theta, the x-coordinate is the cosine of the angle, and the y-coordinate is the sine. Hopefully you don't get those mixed up, right? They go in alphabetical order. X comes before y, c comes before s, right? So that's how you know which is which. And you should know all the other trig functions as well. They're all derived from sine and cosine. For example, tangent is sine over cosine. Right? Cotangent is 1 over tangent, which is cosine over sine. You should also know that secant of theta is 1 over the cosine of theta, and cosecant of theta is 1 over the sine of theta. So these you really should know by now. What else? So there's really not much else. Of course, you should know the standard angles, right? You should know the values of all 6 of these functions for theta equals 0, right? Pi over 6, or 30 degrees, pi over 4, or 45 degrees, or any multiple of these, right? Any multiple of those two angles. So 60 degrees, 90 degrees, 120 degrees, and so on. Right? And 0 radians is also 0 degrees. That's the only angle that's the same for both. Right? So yeah, you should be comfortable with both radians and degrees and be able to convert from one to the other very quickly. I would say most of the time we're going to use radians. Occasionally we will use degrees, but more often than not, radians. Right, that's the way to go. At least in math, we prefer radians for reasons that I hope your pre-calc instructor explained to you. Okay, so you know, there's a whole bunch of identities, a whole bunch of equations that, you know, you may or may not have had to memorize. If you took pre-calculus with me, you know, I do make you memorize everything up here, but I don't make you memorize, say, the double angle formula for sine. You know, this is one that will come up occasionally, so it's good to know, but if you don't, well, the whole point is you can look it up, right? You know, and if you need it on a test, I'll give it to you. But this is one that you probably have seen many times, and you may even remember it by now. The one equation that I think you really should know out of all those identities is this one here, because this one also comes up quite often. Right, sine squared of theta plus cosine squared of theta equals 1. This is the Pythagorean identity. So this is one I suspect you really should know by now. So this one I'm not going to give you that one. That one you should know. Right, and all the variations of that too. So 1 plus tangent squared is secant squared. And you can get that just by dividing both sides of this by cosine squared of theta. And if you divide by sine squared of theta, you get, oh, wait a minute, I think I got it backwards, right? You divide by sine squared theta to get this. Right, so this is, yeah, if you divide by sine squared. No. I had it right the first time. I'm sorry, I'm a little confused. Yep, if you divide both sides by cosine squared, you get 1 plus tangent squared is secant squared. If you divide by sine squared on both sides, you get 1 plus cotangent squared equals cosecant squared. So these come up too, but not as often as this one up here, right? So, but the point is you can always get from one to the other, right? Just by dividing by cosine squared or sine squared. Which one is which? You know, even I get confused by that, obviously, but you know, do both and you'll get both relations here, both identities. All right, so that's the extent of my trigonometry review. And if you're a little bit fuzzy on any of this, the book has a nice chapter, chapter P, which is for preparation, right? And it's essentially just a review chapter. So feel free to look up anything in that chapter. It goes into more detail about lines and functions and some trigonometry as well. And yeah, so if any of this is fuzzy, you can always go back to that. And I would encourage you just to flip through it and to see if any of these concepts are familiar. If they are, great. If not, then spend a little time going through it before we get to the really heavy stuff in chapter 1. Yeah, so that'll be my review. And now we should look at some examples which illustrate the difference between algebra and calculus. Okay, so here's an example straight out of the book, straight out of the exercises, and this probably was for homework, so I would encourage you to try it first, right? Pause the video, work it out, and then let's see if you got it, right? So find the distance traveled in 15 seconds by an object traveling at a constant velocity of 20 feet per second. Okay, so obviously the question is asking if you really understand the relationship between, say, speed or velocity. Again, they use the word velocity here, but I would say speed in this case because it is positive, right? So the speed of an object is just the distance it travels divided by the time that it takes to go that distance, right? So distance divided by time, right? And in general, you have to be aware that this is the average speed of an object, right? On the other hand, if the speed is constant, then the average speed is the same as the speed. So we're not going to make that distinction at the moment, but that will become important later on, right? So if you want to know the distance you're traveling, just multiply both sides by the time. And so we get distance is just speed times time. Rather than use an x, we'll use parentheses, right? Yep. So this problem should be pretty simple. We want to calculate the distance. Just multiply the speed. The speed is 20 feet per second. And the time is 15 seconds. So 20 times 15 is 300, right? And notice the units. We get feet times second divided by second. So seconds divided by seconds, well, they cancel, right? And you get 300 feet. So that's the distance, and we're done. Okay, so hopefully you got that, because that's all this is, right? This is a very simple problem. The next one is not so simple. Okay, so now we want to find the distance traveled in 15 seconds, right? Same as the first problem. But now the object is moving with a velocity of v, which depends on t. So v is a function of t, and it's given as 20 plus 7 times the cosine of t. Right? And you know the cosine function, right? It just goes back and forth. Right? So this is not a constant. Right? In the first problem, it was just a constant, 20. And in this question, yeah, this is going to be a little bit harder. So before we try to tackle this question, let's go back to the first one, right? There's another way to think about this problem here, the first one. So let's suppose I draw the graph, right? So this is the time, and we have, I kind of did this wrong here. Let me try that again. I want to be a little bit more precise here. So here's the time, and here is the velocity, right? So the time is 15 seconds. So 5, 10, 15 seconds. Right? Each one of these is 5 seconds. And then the velocity is 20 feet per second, right? So 5, 10, 15, 20, 25. Okay, and this is in feet per second, right? So notice that the graph is just a horizontal line, right? Because it's a constant function. Constant functions are just horizontal lines, right? On the other hand, if we stop at 15 seconds here, pretend this is a straight line, right? Right. We get, right, the time difference here is the length is 15 seconds and the height is 20. So if I multiply the length times the height, I get 15 times 20, which of course is the same 300. So what am I doing? I'm finding the area of this rectangle. Right? The area of that rectangle is 20 times 15, which is 300. Right? So this is, oops, sorry, I didn't mean to do that. What I wanted to do is write that this is 300, right, square units. But, you know, it turns out to be 300 feet, right, is the area. Right, so you know how to find the area of a rectangle, right? Length times width, or in this case, length times height. Okay. So with that, I think we can make a little bit of progress on this next question here. So for this next question, I'm still going to graph. Again, I need to make my y-axis a little bit longer here. My t-axis a little bit shorter. So 5 seconds, 10 seconds, 15 seconds, right? Now I'm going to have to squash this down a little bit, so the scales won't be the same. So this will be distorted a little bit. Oh, even more than that, yep. So this is 25, this is 30. Okay, so again, this is the v-axis, this is velocity, 10, 20, 30, and so on, right? Okay, so the graph of this function then will look something like this. So I think, right, when t is 0, you're at 27, and when t is pi over 2, I think you're at 20 minus 7 is 13, so right around here. And then right around pi, you're back up to oh, wait a minute. At pi over 2, you're 20. I'm going a little too fast, right? 20. And then at pi, you're at 13. And then at 3 pi over 2, you're at 20 again. And back up to 27. Yep. So the graph looks like this. And then it just repeats itself. So right around here, right, and then right around here. All right, and of course it keeps going, but after all, we're only going from 0 to 15, right? So the lesson for the first example is, all I need to do now is find the area of this region. And that should be the distance that we travel. So you can see, finding the area of this region it's not quite as simple, right? It's not a rectangle. It's not a rectangle at all. So what we could do, of course, is divide this up into smaller pieces that are rectangles. And that's one way to do this, is just to divide this into little tiny rectangles here, and then just add up all those rectangles. So that's something we're going to do, in a few weeks, about halfway through the semester, right? But so without getting into that, sort of the quick way of doing this is to notice that there is kind of a balance here. If I draw the horizontal line v equals 20, right? Look what happens. This area right here that's above 20 should not get counted. On the other hand, we can just easily take this area and fill it in here, because here there's a gap. So if we fill in that gap, right, that effectively cancels this area in here, right? And then you can say the same thing for, for this area here would get filled in over here. And then this would get filled in here, and this would get filled in here, and this would get filled in. Well, here's the issue. We go a little bit too far here. We don't want to fill in anything past 15. So no, this is not going to be quite as exact as we would want. However, if we ignore this piece in here, and it looks pretty small, so the rest of it just forms a rectangle. Of area 3, right? So it's still 15 times 20. Which is 300, right? However, you do have to worry about this little piece in here, which means I think you get a little bit further than that. It should be a little bit more than 300. And I don't remember exactly, but I think it's 303 or 304. It's about 304.55. So this tiny little piece gives you a little bit more than what it should be, right, for them to cancel out exactly. Right, because, well, I mean, maybe that doesn't, maybe I'm explaining it wrong. Let me try one more time here, right? What should happen is that they should balance out, right? But because this red area in here is not accounted for, and it is accounted for up here, there's more area up here than there should be. Right? This area would go down here, which is past what we want. So yeah, we get something that's slightly bigger than 300. And it's about 304.55. But how do you get that more precise answer? We have to use calculus for that. Right? So this is a calculus problem here, this example here. Right? When the area is not a nice rectangle or a nice circle or something like that, then you probably should be using calculus to get the exact answer. Right? So the best we can do is approximate. And if you just said that it's, you know, the same 300 feet, well, you're not far off, right? Right? What are you, like maybe 1.5% error here? Generally not a big deal, depending on your application. 1.5% might be terrible, but in this case, I think it's not so bad. All right, so yeah, again, distance, speed times time. Speed, average speed is distance divided by time. That's going to be very important going forward. So I hope you at least get that from this example here. Okay, and one last example here. So this is also for homework, although I think the one you're going to do is similar to this, but this is an even numbered problem. So if you can do the one before it, the odd one, great. That's good enough. So we want to consider the function f of x, and this is a quadratic function. It's 6x minus x squared. Oops, 6x minus x squared. Or if you prefer, negative x squared plus 6x. Either way, right? And consider the point 2, 8 on the graph. Now, you should be aware that when x is 2, y is 8. So let's just confirm that. We get 6 times 2 minus 2 squared. And 12 minus 8 is indeed 4. 12 minus 4 is indeed 8. So the point 2, 8 is on the graph. And in fact, the first part of the question, part A, is to graph the function. So let's do that, and I'm going to try to graph it, a very nice big function here. I don't know, might be too big, but so x is 1, 2, 3, and that's as far as I think we need to go. Now I'm going to have to change the scale, so this will be a little bit distorted as well. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's as high as we need to go. So I'll just label these for reference. And the graph, right? So the graph will be a parabola, because it's a quadratic function. And when x is 0, y is 0. So I think we can, for sure, start at the origin. When x is 1, y is 5. When x is 2, y is 8. Well, that was given. And when x is 3, y is 9. So the graph should look something like this. And bear with me. I'm going to try to do the best I can here. That's not going to work. Oh, this is going to be really hard. In fact, what's going to happen later on is they want the values for 2.5 and 1.5. So why don't we just get those right away? What's f of 1.5 and f of 2.5? So 6 times 1.5 minus 1.5 squared. You can use a calculator for that. Yeah, I got confused a little bit. It's 6.75, 6 3/4. Right. So that's going to be right about here. And for 2.5, 2.5, you get 8.75, right, which is almost close to 9, right? So this should help a little bit, and I'm going to try to draw it again. All right, close enough. Close enough. All right, and let me label the important points here. So the point P is right here. This is the point 2, 8. And I guess I'll call this point Q for now. Well, I'll call it Q2. And it's the point 2.5, 8.75. So that's this green point right here. And then the red point right here This is point Q1. Or why don't I just use A and B, right? So this is point A, and then the green one will be point B. Oops. All right, so we have our 3 points now. This is 1.5, comma, 6.75. All right, so we labeled those points, and we also want to graph the secant lines passing through the point 28 and the point when x equals 3. I'm not going to do that one. If you want, you can do that one yourself. I'm just going to do the 2.5 and 1.5. For our purposes, that's probably all we need to do here. So connect the line that passes through P and B. Try to make it straight. I mean, you can see it's almost the same as the graph. So it's that line there. And then the red line passes through the point P and A. So that's that line there. It's a little crooked. Let me try one more time here. All right, close enough. All right, so we'll just call it line A and line B, even though these are points. Right. All right, so that's part A. I think we have everything we need here. So part B, find the slope of each secant line. Okay, so yeah, a secant line is a line that passes through 2 points, right? Sorry to make you dizzy there, but all right. So part B, we want to find the slope of each line, of lines A and B. So let's start with A. Yep, so slope of line A. Well, how do you calculate slope? That's something you should know by now. y2 minus y1 over x2 minus x1. Rise over run, right? So which you want to call your x1 and y1 doesn't matter. I'll call this x1, y1. And then for point P, this will be x2, y2. But we could have switched them if you wanted. All right. So just plug in the numbers. y2 is 8, y1 is 6.75, and x2 is 2, and x1 is 1.5. So what do we get? We get 1.25 divided by 0.5, which I think is 5 over 2, right? Or if you prefer, right, 2.5, 2.5. So that's the slope of this red line. It's 2.5, which is pretty steep. And if you're looking at the red line and thinking, well, to my eye, that looks like it's closer to 1, right? When you have a line that's, 45 degrees, that's a slope of 1, and that looks pretty close to 1. So how am I getting 2.5? How does that make sense? Right, so let me remind you of the scale here, right? Look at the x's. This is not 1, 2, 3, 4, 5 like it is on the y-axis. Remember, the y scale is squashed, so this is distorted. This is going to be shrunk down a lot more than it should be. Right. So if I were to do the graph properly, it might look more like this. Right? And now the red line would look more like this. Right. Actually, I got to do even better than that. Hang on, I erased the 5 here. Yeah, it's even steeper than that, right? So it's more like this. Right. And then the red line should look like this. Pretend it's a line, right? It's pretty steep. I'm going too fast and getting sloppy here, right? And then the green line is not, you can see it's not quite as steep, but it's still going to be fairly steep, right? So it's going to be 1 or maybe a little bit bigger than 1. All right, so that's what it should be. So the reason why it doesn't look right is the y-scale is a little off here. That's all. So trust your math, right? The slope is correct. It is 2.5 for the red line, for line A. Okay. And then for line B, so that's the green line. So slope for line B, again, same formula, y2 minus y1 over x2 minus x1. So y2, well, okay, so y2 and x2 is 8 and 2 respectively, so this will be x1 and y1. So y2 is 8 minus 8.75, and then x2 minus x1 is going to be, let's see, 2 minus 2.5. So we get negative 0.75 divided by negative 0.5, which is 3 over 2, right? So this is 1.5. So it is bigger than 1, and I know the green line looks like it's less than 1, but that's, again, because of the scale. Okay, so yeah, the slope of the green line is indeed 3 over 2, or 1.5, 1.5. All right, part C. Use the results of part B, what we just did, to estimate the slope of the tangent line to the graph of f at the point 2, 8, and describe how to improve your approximation of that slope. Okay, so first of all, what is a tangent line, right? If a secant line passes through 2 points, a tangent line passes through 1 point. Right? And in fact, passes through is a little bit not quite as descriptive, right? It really just touches the graph at that 1 point, right? So, yeah. So let's say this is my curve here, right? And I want the tangent line at a specific point. Let's say at this point right here. So the line that's tangent to that graph will look something like this. Right? It just touches the graph at that 1 point without actually crossing through it. Okay? Right. So, right, if you draw a secant line, let's say the line that passes through these 2 points here, you get this line, right? So the blue line is a secant line, and the yellow line is a tangent line. What that has to do with, the tangent function and the secant function for trigonometry, I don't think they have anything to do with that, right? So tangent and these are just names of lines. Don't get confused with trigonometry at this point. I don't think they have anything to do with each other, as far as I know. Okay. So yeah, the tangent line at P, and I'll draw it as a yellow line, will be something like this, right? So it's kind of hard to see here, but it's just touching the graph, and it's somewhere between the green and red lines, right? We'll see that in a minute, right? Yeah. So tangent line passes through 1 point locally. That's the key word here. Sorry, that's an A, locally. So here's the problem. A tangent line can cross a graph more than once. It can cross at 2 points, right? Let's suppose this graph here really did this, right? So look what happens. The tangent line here, if you continue drawing the line, it will eventually cross the graph somewhere else, right? That doesn't make it a secant line. It's still a tangent line at this point right here. Okay? The point is, it doesn't cross the graph nearby. If I look in a small neighborhood of that point, it only touches the graph once. You have to go much further away to find a point where the tangent line will cross the graph somewhere else. Okay? So, yeah, so a secant line has to cross more than once, has to cross twice. A tangent line can cross a graph more than once, but not nearby, not near the point at which you're finding the tangent line. If the tangent line is at point P, then nearby that tangent line can only touch the graph once, near P. Okay, so that's subtle distinction, but I hope that makes a little sense. All right, so can we estimate the slope of the tangent line? Right, so let's use yellow here. So let's call it T for tangent line. Well, we have the same formula, y2 minus y1 over x2 minus x1. But here's the problem, right? The graph only touches the graph once. At least for the blue graph, it only touches the graph at the single point, at the point 2 and 8. X is 2, y is 8, right? Well, so all I can do then is use x1 and y1 is 2, 8, right? But then that's the same as x2 and y2. So what do I get, right? I get 8 minus 8 for the numerator. I get 2 minus 2 for the denominator. So I get 0 divided by 0. And if you remember what I said earlier, that's nonsense. That's not the slope. 0 divided by 0 is not an answer. It's never a correct answer, right? Unless the question is what is undefined or indeterminate, right? So this is indeterminate, right? So the slope could be anything. The slope could be anything. But look, it's a line. It has a slope. We just can't find it using this formula. So this formula kind of breaks down. It doesn't work for tangent lines. It only works for secant lines. Works for secant lines quite well. But it does not work for tangent lines. So let's go back to what I said earlier, right? The yellow line, the tangent line, is between the red line and the green line. So if the green line is the lower slope, right, that's the slope of line B, that was 1.5, and the slope of line A was 2.5, so it stands to reason that the slope of the tangent line has to be between those two numbers. So whatever the slope of the tangent line is, it's somewhere between 1.5 and 2.5. Okay, so take a guess, right? What's between 1.5 and 2.5? Right. Your guess is as good as mine. Right. How about 2.3? Right. Although looking at the graph here, it looks like it's closer to line B than line A. Maybe. So maybe it should be closer to. Oh, no, yeah, well, line B is 1.5, right? The slope is 1.5. So maybe it's 1.6 or 1.7, right? Or maybe 1.8. I don't know. I'm just guessing, right? So yeah, that's kind of a wide spread there between 1.5 and 2.5. There's a lot of possibilities, right? Or maybe it's exactly halfway between, right? Maybe it is exactly 2. Could that be? Could it be exactly 2? Sure, why not? Right. In fact, spoiler alert, it actually is exactly equal to 2. But we don't know that, right? That's not obvious from the graph. The graph is obviously very sloppy at this point, and it's very difficult to determine the slope of the tangent line with any precision here. Okay, so why is it exactly 2? That's a calculus problem, right? So this is really a calculus problem at this point. You know how to find the slope of a secant line because you're given 2 points, and so you just use the usual formula for slope. You've been doing for years now. But to find the tangent line, that same formula doesn't quite work. Okay, so before we can even think about using a formula like this, we need the concept of a limit. So that's going to come up in the next section, in the next video. But for now, the best we can say it's between 1.5 and 2.5. And if you guessed that it's halfway between, then you happen to get it right. But if you said it's 2.1 or 1.93 or something, good enough, right? Now, can we improve on that? Can we improve on the precision here? Well, sure. And here's the idea, right? If we zoom in on this point right here, right, instead of using point P, which was 2, 8, and point A, which was, oh, well, let's use B, 2.5 and 8.75, right? Point B was 2.5 and 8.75. Right, and that's a B, not a D. Right. If we zoom in on that part of the graph, so I got to draw a much better graph here. So the blue graph might look something like this. And the point P is still, let's say, right about here. And point B is way over here. So we got the graph of the, oh, I'm sorry, the tangent line will look like this. Nope, cannot cross the graph. Oh, hang on, it's really hard for me to draw this. Let me start over here. Okay, that looks a little better. So that's the tangent line. We're looking for the slope of that line. And what we had here was the slope of the green line. All right, pretend that's a line. So that was our line B from before. Yep. So there's no reason to use a point that far away. Why did we use 2.5? Well, because that's what the book told us to use, right? That was given. But why don't we use another point? I'll call this point Q, and just use a point that's a lot closer to P. How about 2.1? Or how about X is 2.01? And then Y would be what? So if we plug that into the original function, we get 6 times 2.01 minus 2.01 squared. And plug that in your calculator. Right? And so I get 8.0199. 8.0199. So that's just the Y coordinate, right? So that point is really, really close here, almost indistinguishable. So now when you draw the secant line, the secant line will look a lot more like this. Right? It'll be very close to the tangent line. Not quite, but close enough. Right. So, right, let's use this as my x1, y1, and this will still be x2, y2. So now to get the slope of that line, I'll call this line Q. We use the same rise over run that we've been using here. Right, so y2 is still 8, y1 is 8.0199, x2 is 2, and x1 is 2.01. Okay, so what we get is negative 0.199, nope, 0.0199, 0199, and then we get negative 0.01. And so plugging that into your calculator, your slope should be positive 1.99. Well, that's awfully close to 2. So at this point, I think we can almost conclusively say that the slope of the tangent line is probably 2. Okay? Because the line Q and the tangent line are very close together already. And so the slope of line Q is just slightly under the slope of the tangent line, slightly less. Okay, so how can you make an improvement? Bring your point closer. Make a point that's, instead of farther away, make it closer. Right? As close as you want. You can even get closer, right? You can say instead of x is 2.01, you can take x to be 2.00001. Right? And you can imagine what would happen. Your slope then would be, and this is still a secant line, right? It's not the tangent line yet, but your slope would be 1.99999, which is even closer to 2. So that should be even more convincing that we have the right answer, that the slope of the tangent line is very likely exactly equal to 2 here. Okay, but how do we know for sure, right? How do we know that at some point, if we get even closer, that the slope of the tangent line might not be this, which is very close to 2, but it's not exactly 2. Right? So, yeah, you're right. We don't know that, actually. This could be the slope of the tangent line. And that would, that would be highly crazy at this point. It'd be kind of crazy because it's like it's fooling us, right? It's so close to 2 that, look, it should be 2. The fact that it's not 2 seems wrong to me, right? So at this point, you'll have to take my word for it that it is exactly 2. It's not some crazy number that's just really close to 2. But to figure that out for sure, we need calculus, and we need the idea of a limit. And so I think this is a good point here to stop. And in the next section, we will talk in much more detail about limits. So I'll do that quick refresher on Zeno's paradox, and we'll get into limits, calculating limits just by using numerical tables and by using graphs. Okay, so that's up next.